So today we're going to talk briefly about AROC and IROC. So AROC stands for average rate of change, and IROC stands for instantaneous rate of change. You'll hear me use these acronyms throughout the course of the year. So what we want to do is think back. Okay, not that far back, but let's review what we know. We know that average stands for the mean or the average. So the average slope is delta y over delta x. The slope at a point is the limit as h approaches 0 of f of a plus h minus f of a all over h, because you're getting your slope to be infinitely closer to the point where h is 0. So these two get mixed up a lot by calc students. So what I want to do today is just kind of create some clarity for you. Average velocity is the total distance over the total time. So the velocity average is total distance over total time. Average slope and average velocity are very similar. Instantaneous velocity is like instantaneous, or the slope at a point. Instantaneous means in that instant, or slope at a point. Velocity equals slope. It just depends on if we're talking about average or instantaneous. So your velocity, you need to think derivative, slope, rate of change. You just need to determine what type of slope or rate of change you're looking at. And that's what today is all about. Thinking about what we are asking. So go way back in the day to rate. You were taught rate was equal to d divided by t. Rate equals distance over time, or d equals rt, that the distance was equal to the rate times the time. You'd be given an example such as if I were traveling down a road and no one saw me, and all they know is that it took me 20 minutes to drive 10 miles. They have no idea if I stopped at a red light, if I sped up, if I passed a car, if I slowed down. What they do know is my rate. They know the distance and they know the time. So they could determine that my rate was equal to my distance divided by my time, where my distance was 10 miles and my time was 20 minutes. Or they could determine that I went a half a mile a minute. If I were to ask you to calculate speed, we never talk about miles in terms of minutes. We talk about them in terms of miles per hour. So you would convert miles to minute to miles per hour. So we know that there are 60 minutes in 1 hour. So what that means is they were traveling about 30 miles per hour. Does it mean they were only traveling 30 miles per hour? No, because this isn't their instantaneous rate, it is their average rate. So it's saying on average, this person traveled about 30 miles per hour. Speed limits sort of function as average rates. So in calculus, we like to look at formulas in terms of functions. So in terms of a function, we need to convert the change in distance over the change in time to a formula. So that's when somebody said f of b minus f of a all over b minus A, which transformed even further by talking about the change in position. This should look like a very important formula we've been talking about, which is the slope of the secant. And we've altered the form for the slope of the secant slightly, or we transform it back to slope in the olden days, which was y2 minus y1 over x2 minus x1. But mathematicians like to take this one step further, and they like to say, okay, that's still too broad, that's still too general. I want to know if I'm talking about point A, I want to get closer and closer to point A, where I talk about B being A plus H. So I want B to represent the beginning A, H units away from A. So instead of saying f of B, we want to talk about f of A in terms of H units away from that. So that created the f of A plus H minus f of A all over A plus H minus A, which we know simplifies and reduces to f of A plus H minus f of A all over H. Hopefully that looks familiar. That is our average rate of change, or our slope of the secant. The definition of the derivative is to find the instantaneous moment in which that occurs. So the instantaneous rate of change is that instant, or the limit, as h approaches 0, of f of A plus H minus f of A all over H. And if we go back to the top one, the f of B minus f of A, well, then this would be like finding the limit as x approaches A, because we're trying to get that point as close to that point as possible, where it becomes f of B minus f of A all over B minus A. So again, this is our definition of the derivative. That's the form we see most often. And then this is a variation of that alternative form. So let's consider a graph of displacement, or thinking of it as distance traveled versus time. Here's my D, here's my T. So I know that rate is equal to distance divided by time. So that means the slope from point A to point B would be my velocity. So the average velocity would come from the change in position over change in time. In physics, we talk about position being delta S, or S of t. So our delta S is the change in distance over delta t, change in time. So the average, or the slope, is that delta S over delta t, or t plus delta t. You can see how this looks like our slope of the secant on the previous slide. The speedometer in your car does not measure average, but instantaneous. So our speedometer is our instant velocity. It is the velocity at that singular moment, or the limit. Velocity is the first derivative of position. Velocity is the first derivative of position. All you need to know is AROC is f of x plus h minus f of x all over h. And IROC is f prime of x, where you're talking about the limit of the AROC. IROC is the limit of AROC. These definitions are true for any and all functions.